All right, we should be live. Can you just confirm in the chat if you can hear me clearly, if you can see the screen? Welcome to the first ever live session on geospatial data science on my channel, and I'm really glad to have you here. Can you just make sure you can see me, hear me, and I'll be monitoring our chat really quickly. Um, just 1 second. I just want to make sure everything is fine because I cannot hear you. Let's see. And I'm really glad to have you here. Okay, seems like we're going well. All right, this is going to be a very much a jam-packed session. And while we're waiting for the next 5 minutes, I would love for everyone to introduce yourself in a single message so that it's not separate messages. Feel free to add in your name, organization, the country you're calling in from, and the environmental issue that you're most passionate about. And trust me, I will get back to this at the end of this session because this will connect with what I'm working on currently. So again, add your name, organization, country. Feel free to add your social links like LinkedIn if you feel fine with it. And I really look forward to connecting with you and connecting you all together because what I'm trying to do is build a network for local climate action informed by data. And I'd love for you to be part of that. And I'll talk more about about it at the end. So let's see what's coming in. I'm monitoring the chat live. Thank you again for your responses. All right. Spain, hello. India, Canada, welcome, welcome, welcome. Yeah, feel free to introduce yourself while we wait for the next 4 minutes. All right. Ghana. Okay, we have someone from Ghana calling in. By the way, in terms of registration, we had over 800 people sign up for this session. I'm not sure how many people will actually join, but 800 was very much overwhelming and a really, really great response for this first session. So I'm very thankful for that. Awesome. Colombia, hello. Senegal, India, awesome. Lesotho, okay, wonderful. So we had many people sign up from US and India, but also the distribution is over 75 countries. Yeah, so it's been insane. Okay, hello from the UK. Hello. Great. Keep it coming, guys, because I really would love for you all to connect with each other and focus on similar problems that you might be passionate about. So if someone's passionate about air quality, say in Delhi, India, another person might be wanting to do air quality monitoring in Bangladesh. They might connect and do the same, create a tool that works for both cities. So this is why it's important. Watching from Delhi, okay, awesome. And interested in mapping pollution in Yamuna and smog, okay, wonderful. Hello from Pakistan, welcome. Great. All right, keep it coming. We'll get started in a couple minutes as people roll in. Let's see. All right. So this is going to be a very much information-dense session. So if you have a notepad or want to take notes or even type up on Google Doc, it's fine. But I will be sending links over, so you don't have to save these links. But if you do want to take notes, I would definitely encourage it because this is going to be very dense. And a lot of examples, real examples, are going to be shown in this session. So, all right. I'll wait 1 more minute for people to keep joining. But yeah, looks like so many of you are interested in various topics, and it's wonderful to see how, you know, international and diverse this audience is, and really, really thankful for doing this. Hello from Mexico. Okay, welcome. Kathleen, I see you from Montgomery, Alabama. Welcome. From Bhopal, Delhi. Okay, keep it coming. Awesome. And again, feel free to include your organization and the environmental issue you're most passionate about solving. because this might enable people to figure out similar interests and hopefully connect with you. I'm going to make this connection process way more efficient, so you'll see that in the end. But stay till the end because I do have some giveaways and things that you might be interested in and benefit you in your journey to pursue geospatial data science and GIS. So make sure to stay. All right, we'll get started. Keep the intros coming if you want. All right. So welcome to this session on From Classroom to Climate Impact. This is an overview of my geospatial data journey with real-world examples and tools that you might need. And I hope to provide a lot of value with resources through this session, including real applications, real tools, and advice that is from the industry experience. Okay, so a little bit about me. I am currently the executive director at my company, PlanetSapling, that I founded. And PlanetSapling is focused on leveraging satellite and sensor data to map climate and biodiversity risks, mainly for the purposes of climate change mitigation, adaptation, and conservation. I do not want to map climate risks for investment bankers or figuring out whether it's a good area to invest or not. This is meant for mitigation, adaptation, and conservation. So this session is brought to you by PlanetSapling. This is my company session. And I'm also the director of operations at a Huntsville, Alabama. That's where I'm located. Huntsville, Alabama-based nonprofit called Mycelium. And you might know Mycelium is the network of from which mushrooms emerge under the soil. And Mycelium connects trees in an old-growth forest and exchanges nutrients. So Mycelium, the nonprofit, is focused on accelerating the circular economy through open source solutions meant for waste management, food resilience, and self-sufficient housing. So we aim to create these open source technical solutions that anyone can pursue for creating self-sufficiency, food resilience, and waste management. I'm also a former NASA Impact associate. I worked for Impact, which is a team of the NASA Earth Sciences Division. And as an associate, I conducted projects on detecting floating marine debris, identifying aircraft contrails that do contribute to warming of the atmosphere using satellite imagery, and also did a lot of satellite data management for NASA's Earth data. My background is in physics and earth science from the University of Alabama in Huntsville, and I'm currently studying a master's program of biomimicry at Arizona State University. And the hope is to learn about lessons from different species and ecosystems and apply nature-based solutions to environmental challenges. So many people ask me, how did this journey begin? Why did I become passionate about environmental issues? And that starts with my life in the city of Mumbai in India. I lived for 10 years in Mumbai from the years of when I was 7 to 17. And I witnessed on a very much daily basis air pollution, water pollution. These are images I took of plastic pollution on the streets, landfills overflowing, sewage in the river. And this led me to ask the question, how can we humans live in a manner that doesn't harm our environment, that doesn't pollute our environment? How can we live so that we live in harmony with nature and hopefully restore our environment or even regenerate and increase abundance in nature? And so this led me down the journey of pursuing environmental science. And many of you might resonate, especially if you're living in certain Southeast Asian countries, in South America. I've seen and traveled the world, and I've seen similar stories in many cities across the world. And unfortunately, this is a reality of many developing nations due to colonialism, due to population, due to lack of waste management, and so forth. And we hope to reverse this and be part of the solution. So that began my journey into connecting more with nature. The first image is me with friends and foraging chicken of the woods mushrooms. If you haven't had that mushroom, I highly recommend it because it's extremely delicious. Then I helped kickstart a college club called the UH Green Club. It was restarted, and that focused more on waste reduction, self-sufficiency, energy efficiency, food sustainability, and so forth. The third image is me volunteering at a beach in Mumbai for cleaning up plastics because after some monsoon rains, a lot of plastics were available and flowed all over the beach. And this is just me helping to clean some of it. And the last image is me with a statue of one of my environmental idols. Her name is Rachel Carson. She wrote The Silent Spring. And this was a very, very impactful and groundbreaking book because it focused on how chemicals, specifically DDT, harm pelican eggshells and affect other species and ecosystems. And ultimately, this is the book that led to the banning of DDT. So her impact was super great and wonderful, really inspirational. So this is just a bit of my timeline, and then we'll get right into satellite data and GIS and geospatial data. My first GIS internship was at NASA Develop, and it's a program that I'll talk more about later. But I was a part of a project to monitor water hyacinth. That is an invasive species, which was in Lake Victoria of Kenya. And we developed a toolbox to monitor that. And that was my very first intro to ArcGIS and GIS. Then in 2017, while I was in my second year of college, I was immersed for a month in the Amazon rainforest of Peru and Ecuador. And so I got a chance to live with an indigenous tribe in Ecuador and volunteer at a biodiversity tracking center in Peru. And these experiences this was one of my most life-changing experiences because I learned what it means to live on less. I learned how to connect and be more in tune with my surroundings. And this also started my journey about learning what's around me, what kind of plants, what kind of animals, what is in nature around me, because I wasn't as aware of species around me. You might have heard the saying that kids these days can name 10 or 20 brands right off the top of their tongue, but 10 or 20 plants that grow around them locally, it's challenging to identify them or know about them. So this retuned me and enabled this nature connection that I have now, and I'm growing. And in 2019, I completed degrees in physics and earth system science and got my first job in January of 2020 at NASA Impact that I mentioned as a research associate. And I focused more on satellite data management. But in 2021, my favorite project that I worked on at NASA Impact was co-developing a data set and model to detect coastal marine debris. And this was a very cool project because we created a first data set on high-resolution imagery of marine debris and then a model to do object detection on it. And in 2022, I joined a climate tech startup called Climate Engine that focused on climate hazard mapping. And I worked there for 2.5 years, and I worked on developing various risk models like wildfire risk, extreme heat risk, droughts, floods, and even nature risk, which I'll talk more about. But then in July 2024, I decided it's time to start my own company called PlanetSapling and focus on using geospatial data and media services, because I do create YouTube videos, for climate adaptation, mitigation, and conservation. And this is a very, very much mission-driven, community-led, hopefully going to be community-led effort for implementing local climate action. Okay, so a little bit more. I'm also part of the Mayor's Huntsville Sustainability Commission and the co-founder of a documentary series that's upcoming called From Soil to Soul that focuses more on food justice, food sovereignty, and food resilience. So if any of you are interested in that topic as well, happy to chat about it later. Okay, so these are some satellites. I wanted to get right into it because we have so much to cover. NASA has over 150 Earth observation satellites, and I believe a total of over 1,000 satellites orbiting the Earth as we speak. These are some of the main missions, some of the main satellites that we use day to day for geospatial analysis. You might be familiar with Landsat. It's a very famous satellite that has 9 versions. There's Landsat 1, 2, 3, 4, 5, 6, 7, 8, 9 as of now. And then Terra and Aqua make up the MODIS satellites. Then Aura is quite well known for air quality, Tempo for ozone monitoring. So all of these are satellites of NASA that are commonly used for Earth observation. Then there is the European Space Agency's open access satellites that include Sentinel-2, Sentinel-1, Sentinel-5, which is more for air quality monitoring. But these are very commonly used satellites for open source geospatial data. And I wanted to showcase a quick visualization that I find very interesting. This is called the Low Earth Orbit Visualization. And it might take a second to load, but essentially this tool downloads orbits of satellites orbiting the planet, and not just Earth observation satellites, but all satellites, including Starlink, including communication satellites, and so forth. And the green ones are the payloads that are active, whereas the red ones are debris or decommissioned. And you can hover over each of these satellite objects, and you can see that they're actually moving in their orbit in this model. And it's a little slow because it's very heavy. But I'll send a link to this low Earth observation orbit visualization, and you can actually even track specific satellites. So if you do a search of, say, Landsat or Terra, you'll actually figure out where it's orbiting the Earth, and the time is very current as well, or near real time, not exactly current. But it's a really cool tool just to visualize things and play around, and I wanted to showcase this. Okay. Let's get back to the slides. All right. And geospatial data, what does that mean? Geospatial data is information that is linked to the specific location on Earth. Simple. It's location linked data. And this is an image that shows how, like you can layer different types of data together. There's always going to be a base map, either a satellite imagery base map or some base map like Google Maps that tells you about locations. And then you can add layers like land cover, add demographic data, in this case wetlands, topography. So you can make it as layered as you want and do analyses on each of the layer and combine them. But essentially geospatial data is simply location linked data, geospatial. So there are two major categories of geospatial data. The first is raster data that represents the world as a grid of equally sized cells that are pixels. And each pixel or cell has a value that represents a specific attribute. So you could have a raster of temperature data, elevation data. That means temperatures will be assigned to each pixel, and it is a continuous layer of data. And it's best suited for continuous data like satellite imagery, elevation models, temperature grids, or even precipitation grids, doesn't matter. But the most common file types for rasters are GeoTIFF, NetCDF, and HDF. For vector data, these are spatial features that are usually points, lines, or polygons. And unlike raster data, vector data is discrete or disconnected generally. And points define specific locations like cities, lines are more like roads or rivers, and polygons are defining features such as farms or land parcels, lakes, and so forth. And this is more for discrete data, and the most common file types are shapefiles, GeoJSON, and KMLs. Now, this is another visual representation. So vector data is on the top. We can see points, a line, and a polygon of a pond. But the same representation on a raster would be, there would be a pixel grid for the whole area, and then a pixel would be a point in a raster. A line would be a continuous line of pixels within a grid of pixels. And you can see how it works. So this is the difference between raster and vector, and we'll get more into examples down the line. So one thing you have to understand about choosing the right satellite imagery is spatial resolution. And spatial resolution is for rasters and understanding what is the size of the pixel. And you can see here on the left, high resolution means a very small pixel size, meaning each pixel could be 1 meter or 3 meters. And generally speaking, high resolution imagery or very high resolution imagery is expensive and commercial. It's not free generally. And so this looks like a 1 to 3 meter resolution image. You can see the buildings clearly, you can see roads, you can see the cars on it. Then you have medium spatial resolution, where it's between 10 to 30 meters. So something like Sentinel-2, that's from European Space Agency, would be 10 meter resolution. Landsat would be 30 meter resolution. And that's more of the medium or moderate spatial resolution. Whereas low spatial resolution would be something like 500 meters or 1 kilometer. So several MODIS bands would be in that low spatial resolution realm. But each of these, you can't always use high spatial resolution because each of these have specific use cases. So for instance, if you wanted to monitor things like a specific farm or specific roads or parts of the city, high resolution makes sense because it's a very focused and narrow area and you just want to monitor that. But imagine monitoring the entire globe with high spatial resolution. While it sounds awesome and ideal, it can get very expensive, very memory intensive. instead, something like a low spatial resolution data set for global scales or country scales would be more suited because each pixel covers several kilometers, 1 to several kilometers. So that's when you can use low spatial resolution if you have a larger area to monitor. And medium is more for either cities or certain land regions, bioregions even, and that's when you can think about medium spatial resolution. And the other thing you need to consider besides spatial is spectral resolution, and that is each satellite has certain bands, and bands are narrow ranges of wavelengths that are assigned for specific use cases. So for instance, you all know about the electromagnetic spectrum that goes from radio waves to X-rays and ultraviolet and so forth, and gamma rays ultimately. But for satellites, these wavelengths can be anywhere in the middle of the electromagnetic spectrum. So red, green, and blue RGB are your standard visible wavelengths, which you see for on a color satellite imagery. But then you have a coastal aerosol band that's meant for monitoring aerosols. You have the near infrared band that's useful for calculating things like the normalized vegetation difference index, or NDVI, for vegetation health monitoring. Then you have shortwave infrared 1 and 2. These are two wavelengths. And these are super useful for things like algae bloom detection or even floating plastic detection. It's been used before. So wavelength, the number of wavelengths and the number of bands are important to understand how you can use that satellite data and for what purpose. So this is just an example of the spatial resolution differences with the coverage. You have to consider about the spatial resolution, what the satellite data covers. Is it global? Is it just state? Is it just a single country? The temporal resolution is the frequency of revisit, meaning is it coming back to the same area on a daily basis or a monthly basis or an 8-day basis? So depending on your use case, whether it's daily or monthly, you have to choose the right data. And then temporal coverage is something that's how far back does the satellite imagery go? So if you wanted to use, say, this data set, a 6-kilometer data set from 2004 to present, you could not do that because it's only available since 2012. So you could find a similar data set that goes back to 2004 or figure out some smart way to fuse another data set. But I would highly recommend, at least starting off, use the same data set across different time scales because you want to compare apples to apples. Then again, you have to understand the spectral resolution, which is how many bands and what bands are there in a satellite data. And so one other tool I wanted to show you is called, NASA Pathfinders and Tutorials. So NASA has some really great pathfinders, meaning for thematic areas like air quality, agriculture, biodiversity, and disasters and diseases, you have, and more, you have specific pathfinders that guide you on what data to use and for what specific variable. So this is, it helps you find certain data and figure out what tools to use to download them. It helps you prepare them, so pre-processing and so forth, visualizing, download. So again, pathfinders are a great tool to just figure out what data sets to use for which purpose. I will send this link over, but just note down NASA Pathfinders, and this is a great, just a tool for you to learn more and continue this journey. Okay. Now, geospatial process and pipeline. The first step of that is understanding the problem really well. You have to understand and engage with stakeholders to identify what is the problem, what is the desired outcome. And without understanding the problem and understanding how they will use the data, you can't do this effectively. Because oftentimes there's so much data out there in the world. As you saw in even Leo Labs, there are thousands of satellites orbiting our planet. But the data abundance often creates a problem because people don't know what to do with it or how to use it. And to make sure that your data is effectively used, that the tools you create are effectively used, you have to make sure that you understand the problem and the desired outcome. Then once you do that, then you have to acquire the right data, source and identify and collect the necessary data. And I'll show you more tools to do that. Then you have to pre-process data because oftentimes satellite data sets have missing values, inconsistencies, or need atmospheric correction unless it's already corrected. So you have to clean and transform the data if necessary. Then you do more data analysis to explore what insights can be gathered, what potential relationships are there, and finally you create a model for things like extreme heat or disease modeling. This could involve regression, clustering, prediction, whatnot. We'll talk more about that. And if you create a model, you then interpret and validate the model to make sure it's actually exhibiting reality. And once you validate it, once your team agrees, once you like it, the performance, then you deploy and visualize. Oftentimes, people just jump from acquiring data to visualization. And it can be nice, but again, you want to make sure that the work you spend and the work you do is useful to the customer or the end user. Okay, so some places to source data. NASA Worldview is a fantastic tool. If you haven't used it already, what NASA Worldview does is it contains various NASA data sets, and it shows you specific applications that you can use it for. So one example that I like to show is satellite detections of fire. And I know some of you were interested in wildfire analysis when I asked the question on the forum, what environmental issue you'd like to pursue. And so this is fire and thermal anomalies. It shows you hotspots, and each hotspot has metadata associated with it. So let's go to a hotspot. If I click on this hotspot, it will show me what of course the lat long is, the brightness temperature, fire radiative power. That's essentially a measure of how strong or how big the fire is. And then it has each hotspot has a detection confidence. The higher it is, the more likely it is that it's actually a fire. The lower it is, it could be another thing. It could be something like an oil gas flare burning, or it could be a false, like even something locally, a black surface heating up, a parking lot heating up could exhibit a thermal anomaly. So you want to make sure the detection confidence is high. And again, you can explore more of these data sets. NASA Worldview has guided tours as well to explore each thing. So it's not just about fires, it's about atmospheric rivers, surface water extent. You can see night lights, that's exciting, dust storms. And again, I'll leave this up to you to explore, but it's a really great tool to just start to learn about what satellite data sets in NASA you can use for specific applications. Okay, the next thing is Copernicus. So the equivalent of NASA Worldview for the European Space Agency is the Copernicus Browser. And the Copernicus Browser has data collections that are owned by the European Space Agency. So that has Sentinel-1, Sentinel-2, Sentinel-3, 5P, and Copernicus datasets. And again, you can draw, you can make your own polygons and draw. I probably need to sign in, but you can draw your polygons and then select your date and then download specific data sets. And with both NASA Worldview and Copernicus, what happens is you download data sets to your local computer, which means you're downloading a raster file, you're downloading a TIFF file generally, and or netcdf or HDF, and it occupies memory and storage on your computer. The best way to avoid that, initially at least, is to use my favorite tool, which is Google Earth Engine. And Google Earth Engine has over 400 data sets. It will be much more now. And you can use data sets without downloading them locally, which means all of these data sets are stored on Google's cloud server, and you can use anything without downloading it locally. So you don't have cost on memory, you don't occupy your storage, you don't have to wait to pre-process or download data sets, you can just straight away use them. And so let's see, just as an example, a global human modification data set. Each data set will have some description and bands and so forth, and then example code that you can use to visualize it. I highly recommend learning the basic JavaScript notation and code that's used for Google Earth Engine, because this is a super useful tool for prototyping and a very commonly used industry tool to at least make these tools and prototype and initially do geospatial modeling. And with Google Earth Engine, the advantage is that you can do decades of analysis on it. So if you wanted to, say, find the extreme heat exceedance for the last 30 years of Era 5 data, which is the historical climate data, you can do that on Earth Engine without downloading a single byte because it's all stored on the cloud. But can you imagine doing this 30 years of daily data on something like QGIS by downloading it? It's a headache. It'll be a pain. So learn how to use Google Earth Engine and start exploring this. This is one of the best tools to just learn as a geospatial data scientist because it's extremely, extremely useful. And beyond just Google Earth Engine datasets, there is what's called the community catalog, and that has even more datasets on population, socioeconomic data, soil properties, land use and land cover, hydrology, and so forth. So these are all, again, stored on the cloud, so you don't have to download any of it. And it also has citation, sample code, and Earth Engine snippets. So this is all curated by Sam Roy. So big shout out to Sam Roy. We love his work, and I'll send you these links later. But yeah, these are very, very important to keep in mind and learn how to use. And the last thing I wanted to show before the next section is what's called climateengine.org. Now, this is a tool that's free for academic and non-commercial use. But essentially, especially if you're doing climate analyses or want to look at things like temperature, evapotranspiration, precipitation, all these variables, then you can do, I showed you can code it on Google Earth Engine, and it could take a dozen or more lines of code to do that. But on climateengine.org, let's do an example. What I'm doing is visualizing a raster, and I'm selecting climate and hydrology, and there are various data sets within this. Just for simplicity, let's use GridMet. That's a US-focused data set, and visualize, let's say, maximum temperature. So if I wanted to visualize maximum temperature for the last or the month of August, I will choose a custom date range, August 1 to August 31st. And what this is doing is getting the mean statistic for the maximum temperatures over the month of August. So there are 31 values in August of maximum temperatures, and this map will showcase the mean of those 31 maximum values. And I made this layer without doing anything, no code, right? And not only that, you can also make time series graphs. So one of the cities that I love and have lived in, of course, like I mentioned, is Mumbai. And Mumbai has, most of India has monsoon seasons. So let's see, I want to map, I want to get a time series of precipitation over this year, 2024. So I can go select the start date as 1st January. Let's see, January 1. January 1. And then just as an end date, just to keep it simple, let's keep it 31st August. Get time series. And again, I'm not coding anything. You can see I'm just selecting buttons. And this gives me a time series plot of precipitation without having to do any coding. And it's not just this image. You can actually download the data as a CSV. So it gets you the actual data, which is visualized or visible here on a daily cadence. So you can choose all these data sets and get time series of the various variables available in those data sets, and just have fun, because this is a super useful tool just to, without any code, get simple variable analyses, get maps, get raster layers, and all of that for climate analysis without coding. So use climateengine.org. It's free for non-commercial and academic use again. Okay, moving forward. Geospatial data sources include not just satellite imagery, that's the most commonly used one, of course, but also aerial photography, so images taken by planes, which are pretty high resolution, but not covering a large extent like satellites would. Then you have LiDAR data. That's very expensive data to gather, but LiDAR data is a remote sensing technology generating very precise 3D representations of the Earth's surface and vegetation. And LiDAR data is most commonly used for forest carbon monitoring, forestry purposes, species identification, and so forth. In addition, you have vector data like OpenStreetMap. And OpenStreetMap is one of the best tools that crowdsources data on roads, buildings, spatial features. So even any one of us, I could take a building footprint and map it if I know what the building is, and then contribute to OpenStreetMap. And I believe OpenStreetMap covers 86% of the world's roads, which is very high. So they have one of the best data sets on citizen contributed buildings and roads. So it's a great vector data set to use. Then you can overlay other data sets such as census data, demographic data, socioeconomic data from government programs, and that provides value into insights on population distribution, income, race, and so forth. So again, geospatial data sources can be diverse. The best analyses that I've seen, the best studies usually combine many of these together and find something really interesting. Okay, so what are some key skills that you need for getting into this discipline and kickstarting your journey? Most people, even I, started with ArcGIS and QGIS and doing that, but I would highly recommend learning how to program in at least one, if not two languages. My coding languages include Python and JavaScript. Some people do R, that's fine. You also need to know a little bit of SQL. I'll get more into that later. But at least Python, I would recommend learning, because then you can have the power to create your own geospatial tools. You don't have to rely on softwares, and you can do a lot more with Python instead of just learning how to do ArcGIS maps or QGIS. And you can also create Esri tools with Python as well. So and do Python analysis on QGIS. So Python is a must learn, I would say. R optional, but still highly valuable. And then you have to learn how to do data analysis. So ability to clean, explore, analyze geospatial data using techniques like descriptive stats, data transformation, data wrangling is really important. And then spatial analysis. What kind of data structures are there and how to process those, how to use models and build models on those. Because each file type can be different. NetCDFs are different from GeoTIFFs, which are different from ZARs. So learning these data structures is important. And then machine learning algorithms, just at least some basic things like clustering, classification, predictive modeling, supervised classification. These are important things for you to at least know and get to learn. And finally, one skill that's critical in this field is communication. And I mean translating technical communication to non-technical audience. Because oftentimes the end users of your geospatial data tools or services may not have the knowledge that you do in geospatial data science. So you have to learn how to communicate these insights in a manner that's understandable and actionable by your end user. So at least learning how to present findings and collaborate with people from different disciplines is really, really critical. And then, tools of the trade, like I mentioned, GIS softwares, ArcGIS, QGIS are great just to visualize and manage data, but I wouldn't rely only on those. Python and R, I would highly recommend learning at least one of them. My bias is towards Python, but I've met ecologists and other data scientists who use R fairly well, and no issues against that. SQL is important to learn, at least the basic SQL, because you can learn SQL and then manage and interact with many large spatial databases like PostGIS, BigQuery, and so forth. And these are important databases that store vast amounts of data that would not be possible otherwise. So SQL is useful for doing analysis on those databases. And then at least learning the basics of how to manage cloud-based platforms. Geospatial data, like I mentioned, is very memory intensive. Several gigabytes could go in just downloading one image, for example. So a lot of geospatial data in companies is stored on cloud servers, mainly Google Cloud and Amazon Web Services. So at least learning how to play with one of them and manage data on at least one of those cloud-based servers is important. And then I won't go much into this. You can come back to this video anytime you want. It is recorded and live. But yeah, these are some Python libraries that are extremely useful for geospatial analysis, and more at the end. I'll cover a lot more at the end that I'll send you. Okay, and this is again geospatial data visualization. These are some tools that are commonly used, but For open source and free visualization tools, I would recommend just using QGIS, Google Earth Engine. It's fantastic, and Mapbox is wonderful too. Cardo and Esri and are great. ArcGIS is great, but it's usually licensed, and Cardo is especially quite expensive too. So I'd recommend, at least if you're starting off, focus on QGIS and Google Earth Engine. Okay, this is important because a lot of companies think geospatial data is the solution. It's not. Geospatial data can inform decisions, right? But data is only useful if it can be translated into action on the ground. Data itself is not a solution, but a means to implement the solutions effectively. And so please don't ever conflate data as a solution, because it's really not. If you have the best tools, if you're mapping climate risks, if you're mapping wildfire risk, extreme heat risk, but then on the ground, nobody does anything with that information, despite your tool being excellent, it is useless. So data is only useful if it's translated into action. And our responsibility as geospatial data scientists is at least partnering with the right organizations, finding the right people, or if you have time, doing it ourselves to translate our data insights into action. Otherwise, it'll just be a cool data tool and nothing else, right? Okay, so with that, let's get into some applications. I want to showcase specific geospatial applications to inspire you and even help you learn in your journey. So let's start with this section, environmental degradation. So like I mentioned, I worked on a NASA-developed project that focused on monitoring an invasive aquatic species called water hyacinth. And water hyacinth is, economically devastating as well in parts of Africa because boats cannot pass through if it's too dense. And it can also lead to disease outbreaks because it fosters specific aquatic snails that causes a disease called schistosomiasis, and that could be fatal as well. So NASA Develop is this fantastic project, or rather program by NASA that partners with usually local and state government agencies or nonprofits or for-profits even for translating data to action. So if you are in the US or even if you're international, I recommend at least looking into this program because NASA Develop essentially kickstarted my journey into GIS and learning how data can be applicable and useful. So NASA Develop is this program, and I was a part of a project called Detecting Water Hyacinth in Lake Victoria. And that is essentially what we did was created a surface aquatic vegetation detection toolbox. We created a toolbox using ArcGIS at the time that monitored water hyacinth on Landsat 5, 7, 8, and 8. This was in 2016. So what we did was these red spots are essentially where the hyacinth was present in the Winam Gulf of Lake Victoria in Kenya. And this tool was in partnership with an organization in Kenya that was trying to figure out how to reduce hyacinth concentrations and map where they are so they can inform people and create warnings. So this is an example of a tool that we created in partnership with an organization on the ground in this place, and hopefully had some impact on monitoring this and warning people about hyacinth. So this is one example of water quality mapping. The other project that I worked on at NASA Impact is marine debris detection. So a colleague and I created the first ever marine debris data set on Planet imagery. And Planet is a commercial satellite, has a commercial satellite constellation, and PlanetScope is one of the satellites that has a resolution of 3 meters, which is very high. And all of this information is available on this GitHub. It's open source. I'll send you this link again. But what we did was using literature and research papers of boat expeditions, we found where marine debris is valid, meaning these you can see these brown patches are moving patches of marine debris. That includes seaweed, algae, plastics, and even floating wood. And so we label these marine debris with my hand. Like these red boxes are me drawing boxes around these, and then ultimately created a TensorFlow model that would do object detection on marine debris. So at this point, if you feed it satellite data or satellite image of marine debris, it will draw boxes around it and then give you a percentage of the likelihood of it being marine debris. And so this is a marine debris detection project. You could repeat the similar process for detecting any features. You can detect solar farms. You could detect floating algae or sargassum. You can detect burn scars. That's been done by NASA Impact as well. So this kind of process is kind of the same for feature detection in general, where you train a model on a labeled data set of that feature and then do either object detection or segmentation, which means you actually overlay pixels on the object itself instead of doing a box. So this is an open source project that I worked on, and it's out there in the dataset, and GitHub is public. Then many of you were interested in deforestation, which is a really, really important, close to my heart. And I wanted to showcase an application of deforestation that you could use easily. This is created by the University of Maryland, and it shows you historical deforestation between 2000 to 2023. So this layer is a raster that's showcasing deforestation colored by the year it happened. So let's see, if I choose the satellite imagery as a base map, I switch off this layer, we can see here that these are some farms and some places that were deforested because clearly we can see forest surroundings it near the farm. So it's being encroached by farmland. And if I switch on this layer and make it more transparent, we can see that the yellow color represents this was deforested around 2000. The red means it was pretty recent, 2022. The light blue layers are very recent, actually, 2023. So just last year, some patches here were deforested. So this is an application to inspire you to do similar things, or even use this tool to monitor your local area for deforestation. And you could, in theory, create a near real-time deforestation tracker that can track activity or deforestation within days of it happening, or predict. Many researchers have created prediction models to predict deforestation based on where roads and farms are, because that's where it's likely to continue, right? So this, again, I'll send you all of this data, but take note of this deforestation app. And then we're running out of time, so Global Forest Watch is another tool to use. It's fantastic, and it's one of the best deforestation tracking and public tools for deforestation monitoring. Okay, a lot of you mentioned that you're interested in air quality monitoring. So this is a platform by the UN Environmental Program. And what we can see are wind vectors. So these arrows are representing the direction of wind. And these dots are essentially data at air quality monitors, air quality stations, which showcase the concentration of PM 2.5. And PM 2.5, many of you will know that it is particulate matter that's less than 2.5 microns or micrometers in diameter, which means that it's so small that if you inhale a lot of it, it can actually settle in your lungs and in your alveoli, the air sacs. So it causes the reduction of lifespan because of poor air quality. So you can see in northern India, parts of Pakistan, there's air quality and PM 2.5 is way too high, exceeding by over 10 times the guidelines of WHO. So again, this is an application that you can use to inspire or even practically use. But the best way to monitor air quality is figuring out what pollutants do you want to focus on, because air quality is very broad and it contains things like sulfur dioxide, nitrogen oxide, carbon monoxide, PM 2.5, of course, and other pollutants. So what pollutants do you want to monitor? And you can use a combination of sensor data, which is station data in this case, and satellite data. So you can get a broader picture, but then have more focused data points of local monitoring stations. So air quality is critical piece to do applications on, and there are a lot of these applications. This is one of my favorite ones to show. Okay, that's air quality. So now let's move on to extreme events and climate hazards. So at Climate Engine, one thing I worked on and co-developed is a mosquito modeling tool. Some of you actually mentioned that you're interested in monitoring disease outbreaks or mosquitoes. And we created a model essentially for company SC Johnson that monitors mosquito activity. So right now this model is just in the US, but if I were to enter my zip code, which is Madison, Alabama, I can see this is a score of medium activity, meaning it's quite cold outside, so mosquitoes don't like colder temperatures. But if I were to say, let's see, Los Angeles, yeah, let's see the forecast there. So again, it's medium. So right now it's a little cold and cool. But what this model does is it uses temperature, relative humidity, and variable cumulative precipitation to determine how active will mosquitoes be, because mosquito activity depends on humidity and temperature, but then the time they lay their eggs and activity around abundance depends on cumulative precipitation. How much has it rained in the last 2 to 4 weeks? Because mosquitoes lay eggs in stagnant water, and stagnant water develops when there is a lot of precipitation. So we developed this model based on the life cycle of mosquitoes and based on their relationship with other variables, and validated it using a mosquito capturing database, vector base. And so this is a model that we developed for SC Johnson, and in the future with climate change, there are already outbreaks going on. Last year there was a dengue outbreak in Peru and an outbreak in Bangladesh, I believe, and even Argentina. So as the climate changes, as we face more and more extreme rainfall, this mosquito outbreaks could be more and more common, unfortunately. So this is an important use case for monitoring mosquitoes and potentially disease outbreaks. Another tool that I made is for monitoring extreme heat. So many of you were interested in urban heat islands or extreme heat, extreme temperatures. This is the tool to do that. So what this does is, I know that there was a heat wave in Los Angeles in September, early September, the first 2 weeks at least. And what I did was chose the data set time ranges. So start date is 1st September, end date is 1st October. And I created a algorithm that would that would calculate heat index. So it's not just air temperature or 2-meter air temperature, but it's using a combination of maximum temperature and dew point temperature and surface pressure, so to create relative humidity, and then ultimately find out what's called the heat index. That is, how does a person feel? What's the felt temperature, skin temperature, based on the maximum temperature and relative humidity. So if I click on this pixel, what it gives me is the extreme heat frequency. So this is a score between 0 to 1 that basically tells you what percentage of the month was in extreme heat. So the red area is, close to 66%. So 2/3 of that month was facing extreme heat. 2/3 of September was in extreme heat in that region. The blue regions are a bit lighter, so 13% of the month was in extreme heat. So again, you can do this for any kind of extreme event. You can do this for extreme precipitation. You can do this for extreme temperatures, even extreme cold. You can do this. So this kind of tool, I don't have time to go into a lot of details because we just have 10 more minutes, but you can do these kinds of statistical deviation-based analyses for your extreme event of choice. But just make sure to define what extreme means and define, using literature and scientific papers, what are the standard measures for extreme whatever, heat, cold, precip. Many of you were mentioned that you were interested in drought monitoring. So drought monitoring is a little bit complex because every drought type has different measures. You could use drought risk using Standardized Precipitation Index, SPI. You could also use the Standardized Precipitation Evapotranspiration Index, SPEI. If it's agriculture drought, you have to use soil moisture deficit or even runoff indices. So the method of drought analysis varies by the types of drought. So the first thing to do drought analysis is figure out, okay, what drought type are you mapping and for what purpose? And I've linked a bunch of links here. I'll send you these links again. But there are tools that exist already for drought monitoring. There's a global drought monitor, a European drought monitor, US and India have their own drought monitors, and then there's a global database for SPI and SPEI. So I won't click on this. We are running out of time. But drought risk is I developed various drought risk data sets at Climate Engine, and it's a bit challenging. So I would recommend doing this very carefully and doing this for the right audience. That's the key. Figure out the problem, figure out the audience and the end use case, and then develop your data set from there. Okay, let's move on to asset mapping. So asset mapping is essentially mapping industrial sources, point sources of pollution. One tool that I love is called Climate Trace. And what Climate Trace has done is it's mapped global industrial sources of pollution within various sectors. So if I go to sectors and drop it down, you can see agriculture, buildings, fossil fuel operations, manufacturing, and so forth. So let's just click on fossil fuel operations and go to oil and gas refining. So what I see here in the orange are basically oil refineries. And if I click on an oil refinery, it will show me the estimate of emissions of CO2 equivalent in 2022. And we can see the owner, Holly Frontier, the data confidence, and even the source ID. So every refinery has metadata, not just refineries, but even if I were to click on, say, coal mines, then we can get a map of coal mines with refineries as well. So this is a really cool tool to use for asset monitoring, and even if you want to do environmental justice work or emissions monitoring work for your community or country, I would recommend just starting out with Climate Trace. And there's one more tool in addition. Climate Trace is one fantastic tool, but then there's Global Energy Monitor. So Global Energy Monitor has also mapped a lot of infrastructure and assets, mainly within the energy sector, as the name suggests. So you have Global Coal Plant Tracker, Mine Tracker, terminals, gas infrastructure, solar power, nuclear, steel plant. And so every one of these trackers has assets, and just like Climate Trace, you can and both of these data sets are Creative Commons, so you can download them for free, CC by 4.0. But every asset has metadata associated with it, and you can download this as a CSV and go from there. So yeah, this is a fantastic tool. I love Global Energy Monitor. It may not have the emissions data like Climate Trace does, but the locations, the ownership, it's quite accurate in my experience. And I've worked with Climate Trace and used Global Energy Monitor data for oil and gas field ownership and oil refinery ownership, so I can attest to this data. Okay, lastly, I made another app that focuses on mines. In this case, this example is specifically for Senegal, but I've done a global mine data set as well. So what we are seeing here, I will switch off some of these layers to explain what's going on, is let's switch on satellite image view. So let's see. This is a mine in, I think it's a Daiba mine in Senegal. And I'm going to overlay it with polygons. So these are mine polygons that I extracted from an open source data set. And if I click on this polygon, it will show me the mine name, mine owner, commodity mined, and operator. What I've done is created around each mine point, I've created 1, 5, and 10 kilometer buffers. And the reason for doing this is to, in this use case, see how close is it to protected areas. I switch on protected areas, I'll see these green polygons pop up. And these are areas where mining shouldn't be happening because they're protected legally, right? But you can see that there's this intersection here. So it's within the 10 kilometer radius, and even a part of this polygon is within the boundary of this protected region. So you can do these kinds of analyses. Again, these points are vector data. The polygons of the protected areas are also vectors. So asset monitoring and asset-based analysis is generally point or polygon vector-based analysis. And so, yeah, this is an example of how you can actually see and visualize mines and then judge their proximity to protected regions. And some of these mines, like this one, for example, is literally inside a protected region that's technically, from what I understand, that's illegal. So this is a Massawa mine, mining gold. and it lies, let's see, let's pop this up. Yeah, part of this polygon of the green protected area lies literally within the protected region. So you can find this out and then hold companies accountable for whether they're doing something illegal by mining in a protected region. So that's an example use case. This is super impactful as well. And with that, yeah, again, geospatial use cases: understand the problem, acquire the right data, pre-process it if necessary, do exploratory analysis, and then build your model, validate it. Make sure to validate your model scientifically, accurately, and do some statistics around that, and then visualize and deploy it. But it has to be made for the right audience. In this case, I worked on this partially at Climate Engine for a bank that was interested in divesting from mining companies that were doing something illegal based on their nature risk. So I made a pipeline to map mines using and extract company ownership using annual reports and web scraping. And I use large language machine models like GPT API in this case, and extracted text, reverse geocoded the mines, and then did this analysis that I just showed. So challenges and limitations of geospatial data include you might need to make sure the quality is good for certain data sets. Scalability depends on how you design it, but it's very heavy data, so you have to do it efficiently and use external cloud-based tools often to make sure it performs well. And then you can make geospatial analyses as complex as you want, but I recommend starting simple. Start with a few data sets and then add in. So for this mining example, I could add population exposure. I could add income data for this population. So it could add on layers, but the initial mines is done. So you can add complexity, and then effective and intuitive visualizations. Good design is necessary for communicating these insights. Otherwise, if I just added mine point and then added an ID to the point without the name or anything, it's kind of useless because no one understands it. It's not useful. So you have to have good design and make sure that it's useful for the end user. So with that, I'm ending the session. We are 2 minutes away. Please do ask questions because I'll still be on. But what I want you to do now is you can subscribe to my YouTube channel. I'll be doing more of these live sessions, and subscribe. So make sure to subscribe if you haven't already. Hit that red button. Follow me on Instagram at PlanetSapling. And the reason is what I have on Instagram is a PDF of curated resources of specific courses and specific tools, and some of these links I showed. It's in a PDF for PlanetSapling, and I'll send it to you on Instagram, but you have to message me for it. So at PlanetSapling is my ID. Subscribe if you haven't already. The next big thing is if you are interested, I'm going to email you a link to a short form of 3 questions to participate in a global data scientist network for climate action. And what the plan is to actually connect you by theme within your country to people who are interested in your theme. So for instance, if you're in India and interested in air quality, I'll connect you with people interested in air quality within and around India. And you can start learning about air quality and then hopefully making a tool. My goal at PlanetSapling is to then partner your network with an organization and hopefully get a project so you can get funded and do something really impactful in air quality. And that's not just for air quality. It could be fire mapping, drought monitoring, flood monitoring, and so forth. So this is a global data scientist network. I will email you this link. It's going to be pretty heavy and life-changing, potential, hopefully life-changing thing, because I want to enable a global network of local networks of data scientists like yourself working for local climate action. And lastly, this is a Patreon link. So if you want to help support me just for a few dollars a month, because all of this work is kind of heavy, I'm doing Patreon tiers. So these are membership tiers. For just $6 a month to $15 a month, you can help support me. But since you're here on this session and attending, and if you stay till the end, here's a special offer. For $6 a month, you'll get the code and notebooks that I showed. You'll get some exclusive articles and case studies, and you'll get the community access for free, of course, that I mentioned. So you'll get the benefits of $15 a month for $6 a month. So this is a way to just support me and continue your learning as well. So I'll put this in the chat. This is my Patreon if you like it.
All right, we should be
And
live. Can
oops.
you just confirm in the chat?
Whoop. Yeah, sorry. And yeah, I will answer some questions again. So please do stay on. If you have any questions, I'll be answering them now. Okay. Yes, I will be sending the recording for revision and practice. So yeah, and you can go to any timestamp and do that. Can you share any link to access real-time geospatial data? Yes, I'll be doing that. Again, DM me on Instagram on PlanetSapling, and you'll get that curated resource list that I made. Let's see. Awesome. I see some people connecting with each other. Okay, good. Yeah, I will send you. I'll send you a form to fill out if you're interested in becoming a member of this Global Data Scientist Network for Climate Action. I'm calling it Local Sol for now, but the name might change. So yeah. All right. Have you trained models during your work that was discussed in this discussion? Yeah. I worked on the marine debris detection model that I mentioned. That's an object detection model. So, and I've also trained another model that I didn't show, but that's not necessarily geospatial. It's for waste identification of PET versus HDPE versus cardboard and aluminum. So it's more like a smart waste sorting trash model. Thank you. Yeah, I'm really glad many people are saying that this presentation was useful. I try to make it as valuable as I can. So okay, any tools, engines, workflows to analyze global circulation and regional models for land surface? Yes. Um, I have a link in this resource list that I mentioned on GCM and regional climate models for it's not generally land surface temperature, but it will monitor temperature increases using CMIP6 data. So I can send you that, Sai Krishna. Yes, beginner level data scientists should join this because, yes, please, even if you're a beginner data scientist, the point is to get you trained and provide resources and indulge in self-training between these networks. So I hope to have mentors in each region for this network. So yes, if you're a beginner, please, especially if you're a beginner, do join that. Um, let's see. Yeah, I will send out an email with these resources. So I will be following up with more. So please do keep that in mind. Okay, I'll stay on for a couple more minutes. I'm glad. I'm glad, Nikhil and Sandeep. Thank you so much. Um, and yeah, Tanya, how do we join the network? I will send you a form via email. So keep an eye out for an email by tomorrow. And you will fill out just 3 questions because I do want to make sure that people are serious about this network. I don't want to just provide free access. It will be free, but you'll have to fill out a form, a short form. Kobe, I just see, how do you know what's the most important thing to work on at a time? That's a that's a good question. Right now, it is based on. So I'm working as a environmental data scientist and doing contracts for projects. So for me, it's right now what climate action project I get and receive. But I think figure out what you can monetize, and then what's needed in your local community or local space, and then um, I'd say focus on local climate action more than anything else. That's the key here. Oh, someone asked, okay, how LLMs were used to map mines? Yes. So essentially, companies have annual reports and they have their web pages, And basically, I auto downloaded these annual reports, and then within annual reports, there are sections that state what mines does a company own. So it has a section on assets owned or projects being done. And so using LLMs, I fed that text into a GPT and had a prompt that would organize the names of mines, commodity mined, and other metadata. And then using those mine names, I reverse geocoded the mines on Google Maps using a Google Maps API. So extracting text using LLMs and then reverse geocoding using Maps API. That's how we can map it. Okay. Any tools for population migration for I have to check. I don't actually. I haven't worked a lot with population migration. So thank you. I'll look into that. Thank you. I'll follow up on that, Marina. Um, how do you see the future of GIS scientists, especially with the advancement of easier geospatial analysis platform? Would it be worth? I think GIS and geospatial data science is only a growing field. A lot of companies, especially climate startups, are using this data because it is heavily underutilized. I mean, not every climate company even knows or wants to use geospatial data because it's kind of difficult to access, and you have to have certain skills like programming to use it. But I think it's a growing field, and there's so many applications. I just touched the tip of an iceberg with these applications. There's so much more. Health monitoring, water quality, urban heat island. I mean, there's so much more. So we just saw on this presentation, we just saw a brief, tip of what's possible. Mm, 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 mm. AI and ML tools reducing the need for fundamental coding skills like Python. Okay. Yeah, I mean AI, I mean GPT obviously helps with coding, Python and JavaScript both. I use it frequently in my job as well. But I wouldn't rely on just AI. It's not that good just yet to just not know coding and do it because you have to know certain libraries to use, you have to know certain tools to use and specific code members. So, uh, yeah, I would not just rely on AI to avoid learning how to code. You have to know at least basic stuff. And you might not need to learn Python as a whole. You just need to learn Python for geospatial data science. And as I mentioned, this PDF of curated resources has that information. So do send me a DM if you want. Alexandra asks another webinar with other climate. Yes, I will be doing more of these. I'll be doing one more free one on climate-related analyses as well. Link to become a member. Thank you, Emma. Yes. Let's see. Where is it? Here. Here's my Patreon link in case yeah, anyone wants to become a member. And again, you get $15 worth of benefits for $6 just because you attended this session. And even if you don't decide to become a member, you will be invited to this community of data scientists for climate action. All right. Okay, so one more minute. Let's see. Someone asks, monitor local climate environmental change and local climate action. This really depends on where you're staying, so I cannot answer that. But what I'll say is just using the climateengine.org tool that I mentioned, see what trends are in your area. Is it suffering from extreme temperatures or extreme precip or deforestation? And then you can figure out what changes you can monitor and what actions you might need. And regarding climate action, one of my favorite tools, I didn't mention this, but one of my favorite tools for climate action is called regeneration.org. And this has a nexus of all these climate solutions that, let's see, it's loading. But yeah, all these climate solutions that you can imagine within land, forests, oceans, food, so forth, right? And if you look at, just as an example, let's go to mangroves. If you look at mangroves, any of these solutions, they have specific action items for individuals, groups, companies, and then key players who are some action organizations that are actually helping to conserve mangroves. and there are even learning resources for you. So I would say just explore regeneration.org to learn about some of these solutions, and hopefully in your location you can figure out what you can apply from here in your area. So this is a great tool for yeah, local climate action, and I'll send this link over. Um, let's see what else is going on. Okay, any integrated energy modeling tool with geospatial data? Yeah, actually, one tool that I did not, again, there's so much to show in such less time. NASA Power. So NASA Power is providing solar and meteorological data sets from NASA, and this is mainly for renewable energy and building energy efficiency. This is one excellent tool to use. And then even, let's see, I worked on solar energy modeling for Data. I didn't mention that, but that was more of a data science project, not necessarily geospatial data science. But I think I used, let's see, PV modeling tools from, what was it? Yes, Sandia. Thank you. Yeah, this is another tool. Sandia Labs has some really great models for solar modeling, so I would recommend that as well. Um, yeah, but NASA Power has more geospatial prediction. Internship for a company. Thank you, Emma, for asking. But I am actually building revenue at the moment. So once I do that, we can reach back out. But yes, yeah, I'm building revenue. I don't have enough funding just to do that yet. Most of the resources you presented originated from government programs. What is the interest and size of the market in the private sector? The private sector is actually divided into a couple things. So one is the private sector has data companies like Planet. That's let's look at that. Private geospatial companies. A lot of private companies that use geospatial data, satellite companies, are actually there's Maxar, there's Private, there's Planet Labs is one of the best imagery providers. So these are commercial imagery providers, and then companies like the startup I work for, Climate Engine and Jupiter Intelligence, and all of these companies that have climate intelligence, they are actually using open source data for the most part. I will say that they primarily rely on European Space Agency and NASA data. So a lot of data that's free is government funded, and private companies, to save costs, use open source data. And so there's a lot of interest in this market because geospatial data's potential for mapping climate hazards and nature risks is just massive. And yeah, so I can talk more about that in another session, but there's a huge interest from the private sector in this realm to monitor these issues. All right, I will have to leave soon, but thank you so much for joining. Once again, follow me on Instagram, subscribe if you haven't already. That'll help me out, and then DM me for if you want that PDF, and I'll send you a follow-up email with how to join this network. And if you're interested in supporting me and these efforts and gaining a little more, then you can become a Patreon member. So thank you so much again for